Today we are going to discuss one of the most critical yet often overlooked aspect of blast furnace operation. This is not just about a maintenance, it is about preventing a cascade of failures. Today we are uncovering the truth about short taphole. Let's begin. So, why should you care about a few inches of refractory clay? Because a short taphole is not an isolated cast house problem. It's a primary trigger for plant wide instability, serious safety hazard, and massive financial loss. Consider this data point. A single coke mess incident can cost over $50,000 in immediate lost production and cleanup. And if it's happening repeatedly, it's a screaming alarm that your furnace is in distress. The root causes of the short taphole. So, what causes a taphole to get short and wide? It's a battle on multiple fronts. First, chemical attack. The basic slag literally dissolve the acidic taphole clay, and oxygen during casting weakens its very structure. Second, abrasive erosion. Think of coke fines and fast flowing slag as a continuous sandblaster, scoring the walls away. Then, operational practices, incorrect drilling, poor clay quality, or inadequate plugging create a weak foundation that erode faster. And let's not forget physical shocks. The brutal thermal cycling from 1500 degree to ambient and back causes crack and fatigue. uh, Overusing the oxylons just burn it back even faster. Finally, underlying hearth condition can accelerate the wear, making the problems even worse. Now let's get to the core of the issue, the physics of wild flow. It's all boiled down to a simple principle. Flow equals pressure divided by resistance. The resistance of a taphole is proportional to its length divided by its diameter to the fourth power. The little 4 is the key to everything. Here is the data insight. A 20% reduction in taphole length can lead to a 40% increase in flow velocity. These high velocity, low resistance pathway transform a controlled stream into turbulent, uncontrollable torrent. This brings us to the most visible disaster, the coke mess. The mechanism is a powerful Venturi effect. That high velocity flow creates a vacuum at the taphole inlet inside the hearth. The result, the vacuum violently sucks coke particle from the dead man right into the iron stream. Let's look at the impact data. Production loss. Casting must be stopped prematurely. Yield loss, you can lose 5 to 10 tons of coke in a single bad cast. Safety hazard, we are talking about uncontrolled splashing of 1500 degrees centigrade material and significant refractory damage to the troughs. But the damage doesn't stop at the cast house. A short taphole trigger a plant-wide domino effect. The first domino effect, a rapid hearth drainage. Liquid levels plummet, disrupting the protective coke bed. The data shows hill level can fluctuate by over 20 centimeters. The second domino, the gas flow instability. The sudden pressure release chokes the process, causing 5 to 10% drop in CO utilization within minutes. The third domino, the burden descent problem. The erratic liquid level leads to irregular descent, increasing the risk of hanging and slipping by over 30%. Final domino, the thermal and chemical imbalance. the whole heat and the mass balance is thrown off, leading to a wild silicon swing and furnace cooling. Now let's talk about what this really cost. The bottom line, it's costing us money, a lot of it. Here is a breakdown for a single incident. Lost hot metal, 100 tons, that's around 50,000 US dollars. Wasted coke, another 2,500 US dollar cleanup and downtime 25,000 US dollar. Refractory repair 5,000 US dollar. Total per incidence approximately 82,500 US dollar. And if it becomes chronic, the indirect annual cost from reduced campaign life and higher fuel rate can reach a staggering 1 to 2 million dollars per year. You do not have to wait for a full blown crisis. The signs are there. If you know what to look for, this is your early warning system. Monitor these key parameters. Casting time dropped from a normal 90 to 120 minute to less than 60 minute. Casting rate becomes erratic and start very high. Taphole length, the critical metric, it should be 1.8 to 2.2 meter. Anything below 1.5 meter is a major red flag. Then similarly, furnace pressure, uh, furnace pressure if you see, then uh, look for the sudden drop during the cast. So these are the warning signs that operator need to look into while operating the furnaces. Now, so how do we fight back? How do we take back control? Immediate actions are like these. Measure taffle dimension after every single cast. Standardize drilling practices, angle, depth, techniques. Invest in high quality taffle clay with a real erosion resistance. Long term strategies are like these: implement laser scanning for precision, track wear rate to predict failure before they happen, train all crews on recognition and response. This is the team effort. Now, don't just take our word for it. Hear how one plant turned it round. Before, they had 3 to 5 coke mess incidents every month. The average taphole length was a critical 1.2 meter. The annual cost was 1.8 million US dollar. After they implemented strict length monitoring, improved clay quality, and standardized their drilling protocol, the results: zero coke mess incidents in 6 months, achieving 1.2 million US dollar in annual saving. The proof is in the data. For the engineers and the scientists watching here, the fundamental law that governed this entire phenomena, the Hagen Poiseuille equation. This equation proves that flow rate is proportional to the fourth power of diameter. This is the mathematical bedrock of our crisis. A teeny change in diameter has a massive exponential effect on the flow, and that is being demonstrated by this equation. So let's recap the inevitable chain of failure. Short white taphole leads to exponential increase in flow, d to the power 4 law. The Venturi effect and wild flow, siphoning of the coke from the dead man, catastrophic coke mess. The science is clear, the data is undeniable. The solution is in our hand.